In this video, we will analyze the tracking strategies for virtual reality in greater detail. Here are the most prevalent tracking technologies available for tracking: mechanical, electromagnetic, acoustical, inertial, that includes accelerometers and gyroscopes, and optical. We will now explore how each of these technologies operate and introduce their key features. While there are earlier virtual reality devices and patents, even Sutherland experiment with head-mount displays marked the birth of the first functional virtual reality headset. This pioneering device featured a substantial robotic arm supporting the display to track its pose. The arm was equipped with encoders that transmit their data to a computer, which in turn update the display images. It's intriguing to note that the initial functional head-mount display relied on mechanical solution, a far cry from today's technology. This unique tracking system earned the moniker the Sword of Damocles, a reference to the Greek legend where Dionysius allowed Damocles to sit in his throne but suspended a sword above it, held only by a single hair from a horse's tail. This setup symbolized the essence of kingship, abundant fortune intertwined with the perpetual vigilance against impending threats. In this historical video, we can witness the Sword of Damocles in action. The footage offers a glimpse of the encoders in operation and illustrates how users had to manually handle the headset. Encoders are sensor devices meticulously engineered to provide feedback regarding the movement or rotation of an object to a computer system. This feedback empowers the computer system to determine where the tracked object is. In our context, this feedback often translates into updating images on the display. Encoders come in various types, each with its own operational characteristics. They can be absolute, constantly providing the precise position or rotation of an object, or incremental, offering information from a particular movement, such as indicating that the device has rotated an additional 30 degrees since the last measurement. Encoders can be further characterized as linear, rotary, or angle encoders, and their sensing technology may rely on optical data, such as passage of light through specific patterns, magnetic principles, or capacitive methods. The choice of encoder solution depends on specific requirements of your project, including factors like cost, size, weight, and more. Mechanical tracking devices, although high precise with low bandwidth requirements and a high sample rate, are now relatively rare in contemporary applications. This is primarily due to the inherent motion constraints and often cumbersome size. The most renowned mechanical tracking devices are part of the history, with one of the most famous examples being the fake space boom, which we can see in some of the images here. In this setup, users are affixed to an articulated arm, enabling them to visualize 3D information on a display. Some mechanical tracking systems are employed today in haptic devices that simulate force feedback. Examples include the Phantom Omni, which tracks your fingertip, and advanced virtual reality gloves with force feedback, such as those developed by Dexter Robotics. Mechanical tracking becomes essential in this case to enable precise force feedback simulations. Magnetic tracking is a compelling tracking technology capable of sampling in 6 degrees of freedom. It finds applications in various fields, such as medical diagnosis, where small sensors can be introduced in the body for precise monitoring. This tracking method gained popularity in the 90s, exemplified by the devices like the Ascension flock of birds, as shown in the image. The systems comprise 3 orthogonal coils that emit and detect variations in the magnetic field. However, it's worth noting that magnetic tracking solutions can be susceptible to interference from magnetic sources or nearby metallic structures. In modern times, the devices have become remarkably compact, as exemplified by the integration of such technology by the companies like Premo. Today, we can see, for instance, electromagnetic tracking is employed in controllers of the Magic Leap 1. Electromagnetic tracking systems, commonly referred to as EMTS, can accurately determine both position and orientation within 3D space. This technology operates on Faraday's law, which states that when a wire moves within an alternating current magnetic field, it induces a voltage across the coils. This induced voltage is directly proportional to both the winding area and the intensity of the magnetic field. By measuring this induced voltage, it becomes possible to measure both the rotation and translation from the emitter coils. Under optimal conditions and with suitable electronic system in a stable environment, one can achieve high precision detection of both precision and orientation. Moving on to the next tracking system, we use sound waves for tracking. Acoustic tracking devices operate by emitting an ultrasonic pulse and subsequently measuring its echoes. There are two primary techniques employed in acoustic tracking. First one is time of flight, and in this method we send a pulse and calculate the distance by measuring the time it takes for the echo to return. And the second one is phase coherence. In this technique, we update the object's distance by measuring the phase shift of the echo in relation to the last update. It's worth noting that this approach may be susceptible to cumulative errors over time. Okay? While acoustic tracking systems typically offer low-cost solutions, they have certain limitations. They can be sensitive to atmospheric conditions and exhibit higher latency due to the finite speed of the sound. Some products like this from Intersense in the image combine inertial measurements with acoustic tracking to mitigate these limitations. Inertial tracking devices play a pivotal role in the realm of virtual reality, serving as a fundamental component within the majority of VR headsets and controllers. These sophisticated devices are commonly referred to as IMUs, which stands for Inertial Measurement Units. IMUs are intricate systems comprising gyroscopes, accelerometers, and at times magnetometers. Their primary function revolves around discerning orientation that's achieved through the internal gyroscopes, and when coupled with a magnetometer, IMUs can even ascertain absolute orientation based on Earth's magnetic poles, and relative position achieved through the accelerometers. One of the key attributes of IMU is their rapid response time, making them exceptionally precise for short-duration tasks. Nevertheless, they grapple with the inherent challenge, cumulative errors arising from the gradual deviation between the measured values and actual values. Some devices incorporate recalibration mechanisms to mitigate this issue to some extent, but it remains an ongoing concern in their operation. In the images provided, you can observe various products equipped with IMUs, showcasing their versatility and applicability across different devices. These IMUs very often assume the form of semiconductor chips, facilitating seamless integration into a wide array of technology gadgets. Today, nearly every smartphone has an IMU, illustrating the ubiquity and the importance of these devices in modern technology. The predominant technology employed for tracking in virtual reality is optical tracking. Optical tracking often relies on infrared cameras, although visible light can also be used in some instances. There are two primary methodologies for optical tracking, and we are going to start with the more traditional, outside in. In this approach, cameras remain stationary in no positions, while the tracked object maneuvers within the camera's field of view. In the outside-in strategy, it's common to encounter infrared cameras equipped with an infrared light emitter ring, and we use markers that are typically small spheres coated with retroreflective ink. This technology does have some limitations, including susceptibility to line-of-sight issues, ambient light interference, and infrared radiation. In the movie industry, markers are used to track body and face movements, as illustrated here with their usage in the Pirates of the Caribbean movie. Once these markers are identified, they are meticulously aligned to identify the position in 3D. The concept bears similarity with virtual reality, albeit with some distinctions. In VR, cameras are typically stationary and intricately calibrated to enable seamless real-time interactions. Here we have a glimpse of a standard camera employed for tracking markers. These cameras are equipped with LED rings that emit infrared light. Some tiny spheres are organized together in a target, and the sphere reflective surface makes the emitted light back towards the camera. This retroreflective coating uses the same strategy to what's used in road signs to ensure optimal visibility. Subsequently, the captured image undergoes filtering to isolate the brightest spots. This process enables the identification of the 2D coordinates within the camera image where the markers are precisely located. It's important to emphasize that identifying the 3D position of each tracked sphere necessitates the use of multiple cameras. Once this data is acquired, the tracking algorithm embarks on the task of discerning the geometry of the target under scrutiny. Typically, a cluster of spheres is employed as the target, and this arrangement provides valuable insights for deducing the artifact's rotation as well. There isn't a strict rule governing the choice of the target geometry. However, it's advisable to avoid the coplanar configurations to ensure accurate tracking results. There are other solutions for outside-in camera tracking, such as the Kinect. The Kinect has the capability to detect depth information and is very convenient for tracking a full body using just a single camera. A widely adopted and exceptionally precise solution for virtual reality headset is the Vive tracking. The fundamental concepts revolve around emitting infrared patterns into the environment. Subsequently, sensors within the headsets and the controllers meticulously recognize and decode these patterns. Through a series of calculations, it becomes feasible to pinpoint the precise position and orientation of the object within the virtual space. Vive tracking hinges on the utilization of lighthouse base stations, which emit precise infrared flashes and swap infrared light both vertically and horizontally. The sensors embedded with the VR devices have the ability to discern and interpret this integrated pattern, facilitating seamless tracking. This animation provides a visual demonstration of the tracking process. In this video, the sensors get highlighted when the infrared light hits it, and the time difference between the light reaching each individual sensor is sufficient to calculate the object's precise locations and orientation in 3D space. It's important to note that this occurs at a much faster pace. In the context of Vive devices, an inertial measurement unit IMU plays a vital role in maintaining position and orientation updates, particularly in situations where there might be gaps in the infrared tracking data. Finally, the other optical tracking strategy we will discuss is the inside-out. This is the trend in virtual reality today and centers around SLAM, an acronym denoting simultaneously localization and mapping. This strategy uses infrared cameras which scan and perceive the surrounding environment. These cameras initiate a pattern recognition and, in real time, start on reconstructing the environment while keeping identifying new patterns within the 3D space. While this approach isn't entirely novel, it historically requires markers like QR codes scattered through the environment or sophisticated devices such as LiDARs. Today, commodity VR devices use this technology, marking a significant advancement in the field for tracking users' position and orientation. Here, in the Quest headsets, detecting the position of the controllers involves a clever mechanism. Infrared LEDs embedded with the controllers emit light that is invisible to the human eye, but readily discernible by the headset's cameras. After some calculations, the headset then precisely determines both the position and the orientation of these controllers. The latest trend in virtual reality is hand tracking, which uses the inside-out cameras embedded in your headsets. An algorithm continuously processes real-time images of your hands to estimate the position of your fingers. These estimations are then used into a 3D representation of a generic hand. This allows you to seamlessly interact with the virtual environment without the need for a physical controller in your hand. In conclusion, it's crucial to acknowledge that the realm of tracking offers several strategies and possibilities. For example, we can consider the VR treadmill designed for simulated walking, or the utilization of the GPS signals that are particularly valuable for outdoor experiences. Tracking in virtual reality stands as a fundamental component constantly evolving. Emerging tracking solutions promises increased stability, speed, and cost effectiveness.